Welcome back to another Ramda JS video, and in this video we are going to talk about the crazy world of currying. And let's be more specific. We're going to talk about the function curry and the function curryN, because they are essentially kind of the same thing within the library Ramda, except that curry works with non-variadic functions and curryN works with variadic functions. I mean, you can use both on both in some sense, but the intent is that you would use curryN if you have a variadic function. So a variadic function is a function that takes an unknown number of arguments, or not as in an unknown, but a potentially infinite number of arguments. You can just keep passing arguments to the function, and it's still well defined, as in like the function has an implementation. Yeah, I mean, I'm kind of thinking, are we going to talk about currying, like theoretically talk about currying, or are we just going to talk about how to do it in Ramda? And I think I'm going to strike a balance that's very heavy on the let's just talk about Ramda and just talk about how it's useful to do currying, because I actually opened up the Wikipedia page here for currying, and I mean, currying is clearly a deeply theoretical concept that you can keep on digging in, right? And it's, I mean, you can see here from, it's used in functional programming languages, it's used in theoretical computer science, it's been used in math to turn multi-argument functions into single-argument functions, because then they are easier to study and so forth. I mean, for an interesting, what is that called? Like, curio. I can't remember the word, but just like an interesting blurb is that there's a dude called R.curry, which is actually not necessarily, it doesn't seem the person who initially introduced the concept of currying, but it seems clearly his name is the source of the word currying. Anyways, let's leave this Wikipedia page and jump back here to Ramda. If you've watched this series, right? Like, I mean, okay, kudos to you if you've watched the series from video 1 up to this point. Wooza! I hope you feel smarter from a functional programming perspective, because man, have I learned a lot by reading through all of these functions and actually talking to you guys about these. But anyways, if you've done that, or if you've watched a few of the videos, you probably already have a solid understanding of what currying is, because we've used it like all the time, right? And that's the point of currying. It's like, it's so fundamental to the idea of functional programming that after you've started using it, you just stop thinking about it. You're like, of course you curry, and of course you curry almost all the time, right? Or actually, sorry. Let me be specific here, because probably somebody will say that I'm wrong here. So what you do is you partially apply all the time, right? So currying is what enables partial application. So when you curry a function, you take a multi-argument function and you turn it into a series of one-argument functions. But then when you partially apply a function with one argument and get a new function back that you can then apply the next argument to, that you can then apply the next argument to, and that you can then apply the next argument to, and so forth, right? So currying is actually the notion of constructing a function, turning a multi-argument function into a series of single-argument functions. So currying allows for partial application. And if I'm super specific, what we do all the time is that we use partial application in functional programming. But when you're in a language such as, for example, Haskell, every function is a one-argument function, right? Everything is curried, right? So it's reversed in Haskell. It's that it looks as if you are defining functions that take multiple arguments, but actually you're not. That's just syntactic sugar around the idea of applying each of the consecutive arguments one by one, but getting intermediate functions one by one. I don't actually know whether on a sort of implementation basis you actually get like these intermediate functions are actually created or not. I mean, probably there's some compiler smartness going on there that I don't understand. But either way, I mean, all functions in Haskell are one-argument functions, and if they don't look like one-argument functions, that's essentially syntactic sugar, because the idea of having curried functions so that you can do partial application is paramount to a language such as Haskell, and I would say paramount to a functional language. I've now learned that there are actually other approaches, so correct me if I'm wrong here, somebody please in the comments, but Clojure doesn't have currying. They've made a different choice which gives them other benefits, but then the drawback of not having currying. Maybe I'm wrong here, right? But so I just want to add that sort of parenthesis, saying that there are of course other ways of approaching it than currying. So it's not like yeah, I'm not competent enough to say whether that currying absolutely has to go into a language if you're designing a functional language. But anyways, it's clearly very powerful. Okay. Enough talking, right? Let's get into something concrete. So let's read the definition here. So curry returns a curried equivalent of the provided function. The curried function has two unusual capabilities. First, its arguments. Okay, so here they... no, okay. Yeah, okay. So when they say unusual capabilities, I assume that they here mean unusual for currying, right? Not as in they're now describing currying. I think they assume that you understand currying already. But they're saying the curried function has two unusual capabilities. First, its arguments needn't be provided at one at a time, right? So you don't have to call it this way, right? Because that's what we're saying. If you have a function, so if you have yeah, so G here is the function that's returned by calling R.curry on F, for example. Yeah, okay, they actually say here. If F is a ternary function, so a function taking three arguments, and G is R.curry on F, right? So R.curry applied on F, then you get back a function, and let's call that G, right? So essentially what they're saying is like, oh, sorry, let me jump into node there. So they're saying let G equals R.curry F. Right, but we don't actually have F. Let's actually, so let's say R require Ramda require, right? So then we have R, and then let's actually do R dot curry. No, let's define, actually use let. So you define F as a function that takes three arguments, so X, Y, and Z, and let's just define it as X plus Y plus Z, right? So it's the sum of these three arguments. But so F now is a ternary function. If we say the length of F, you can see that we get 3. So if you say R.curry F and store that in G, let's say, then G.length is now actually 3. So that's an interesting thing that they did, right? Because they're saying that you can call it like this. But if they didn't have this, let's say, unusual capability number 1 that they're describing here, the length here would be 1, because G would be a function that you can apply to one argument, and then you get back a new function, right? And then you can apply that to another argument, and you get back another function, and then you can apply that to another argument, and you get back the result of executing the whole thing. Now, so that's essentially partial application. And what they're saying here is then that there are any of these ways of calling it, and any of these ways of partially applying it are valid ways of partially applying it. Or rather, maybe I should say it's something like any of these ways of mixing partial application with, not mixing partial application, but mixing calling it as if it only took a single argument and actually passing multiple arguments at the same time is essentially the same thing, right? That's what they're saying. The second unusual capability that they describe here is that there's this special placeholder value r dot, whoops, now I clicked it. What's going on? Okay, we actually stayed on this. Well, whatever. Okay, so the special placeholder r dot underscore underscore, which we actually talked about in another video. So I'm sorry, I'm pretty confused, but maybe we talked a lot about currying then as well. But that may be used to specify gaps. So allowing partial application of any combination of arguments, regardless of their positions. If G as above is if G is as above, and if an underscore is r dot underscore, then the following are equivalent, right? So this is kind of like saying which arguments do you want to partially apply, right? So if you have this ternary function, now for us it doesn't matter, right? Because f, let's think about it. If you have f at 10, 20, 30, you get 60 back, but that's the same thing as passing 30, 20, 10 like this, right? So let's actually redefine f. Let's say f is we had x, y, and z. Actually, let's not do ternary because it's messy for me. So let's say we have x and y, and then you say x minus y, right? So f, yeah, so f should actually be called sub or something like that for subtract, right? So if you have x and you have y, and the implementation is x minus y, right? So we have a function called sub. If you pass 10 and 5, you get 5. Pass 20 and 5, you get 15. If you pass 5 and 10, you get -5. Okay, fine, it's subtraction, right? All good. Okay. What's the deal with this placeholder thing? Well, sometimes you want to partially apply the function, but you want to partially apply the second argument, right? So think about this function. If I want to say, think about this. Okay, now we're getting into partial application for sure. Let's say I had the list 10, let's actually save that. So let's say we have a variable called x's and we have 10, 20, 30, 40 in this list. Okay, so this is the contents of x's. What I want to do is I want to map over x's, and what I want to map is I want to map the subtraction of 1. What I want to say is I want to say remove 1 from each of these things. So I want to get 9, 19, 29, 39, right, from this list. This is not going to work, right, but we're going to get to this in a moment. So I want to map the subtraction of 1 over the x's. Sorry, not map, r.map. Apologies. Fn is not a function. Okay. Sorry, because I haven't curried the function. So yeah. So let's say. So this is so. The issue here is, of course, that you can't do this. You can't do so. Notice how like intuitive just partial application is when you get used to it. You're like, well, why doesn't this work? Oh, okay, sorry, because my function isn't curried. So we defined sub, right? We defined sub such that it has a length of 2, but it isn't curryable. So we can call sub 10, 20, but we can't call sub 10 and then 20 like this because it's not a function, right? It's not curried. So what we can do then is we can use Ramda's curry function. So we can say let's say c sub, so as in the curried version of sub. Sorry about this, right? And then we say r.curry sub. Okay, so what about c sub then? Can we say 10, 20? Yeah, we can, and then we get negative 20. Can we also do this, right? Where we partially apply it first with 10 and then with 20? Yes, we can, of course, right? And that's the power of this partial application thing. Actually, this is not very powerful, but here's the cool thing, right? So then we can say map. So remember, we had x's, which is this list. Then we can say r.map using c sub, and I want to map over the x's. Okay. Sorry, c sub 1. And then you get negative 9, negative 19, negative 29. Notice that's not what we wanted, right? We wanted 9, 19, 29, not negative, right? So what happened? Well, what happened is that we are mapping not the subtraction of 1. Actually, let's write this out and then it's more clear. So we are mapping, so whenever you have an x, we want to say 1 minus the x. That's what we're computing, and then we're mapping over the x's. This should give the same thing, right? But that's not what we want to do. What we want to do is we want to say x minus 1. That's decrementing, right? We were actually interested in doing decrementation. That's the result that we want. So what do we then do? We can't just say c sub 1, but we actually, because we partially apply, and here is the second argument that we want, right? That's the argument that we want to extract from the list. That's sort of the item in the mapping, but that's our second argument and not our first argument, because the way c sub is structured. So yes, we could define a whole new function that does that has the argument order flipped, but that's madness, right? Because then like this goes for every potential function that you ever potentially define. So what you can do is instead is that you can use this r.__. So you can say, okay, I don't know the value of the first argument, so I want to leave that undefined, and whenever you supply the next, so this is a partial application, and whenever you supply the next argument, I want you to supply it here. But then you can say, I know this argument, however. So the second argument I know, however, and that's 1. So this is going to define decrementation for us, right? And if we run that, you can see we get 9, 19, 29, and 39, right? And this underscore thing is actually, it's a very powerful way of approaching it, because we haven't talked about this yet, because we haven't gotten to flip yet in the like r.flip in Ramda, essentially, right? But flip is also a very commonly used function in functional programming. So, So what you can do is you can also flip the order of the arguments of a function. So you can say r.flip c sub, and then you get back a new function. So if you check this out, if we say c sub 10, 20, actually, why am I always working with negative numbers? 20 and 10, then we get back, actually, let's say 20 and 5, then we get back 15. But if I say r.flip c sub, and then apply that to 20 and 5, so same order of the arguments, now we are not computing 20 minus 5, we are computing 5 minus 20. Right? And that's the reason we're getting negative 15. So we're flipping the function, we're flipping the arguments of the function, the order in which the arguments are applied. But I think this only works with binary functions, right? It works with functions that take 2 arguments. And so if you have a ternary function, for example, which is probably why they're using an example with ternary functions here, then the fact that they're using underscore is of course, the fact that they're using underscore rather than flip is of course a lot more useful, or it's more evident why it's useful, because how would you flip this function? You could probably just flip the 2 first arguments, but then you could do another flip in order to sort of move them. No, you can't. Yeah, but then you could partially apply the first and then flip or something like that, right? But like underscore, when you have more than 2 arguments, is a very, very clean way of partially applying whatever arguments you actually want to apply. And also, I mean, even if you just have a binary function with 2 arguments, sometimes I think it's more clear just to say, well, this is the argument I don't know and this is the argument I know. I don't know, depends, right? Depends on your scenario and whatever you find to be suitable. So the power of partial application, right? The power of partial application is that you can pass around this partially applied function. So now we can define like decrement. We define the function decrement as the flipping of C sub. Let's say, no, yeah, decrement 1, sorry, maybe, yeah, so it depends. I mean, we could define, we could actually just define decrement like this, right? Because then you would say decrement x from y, right? So it's not like sub, it's not like subtract, but yeah, it's, this is a bit funny, right? Like, I mean, naming wise, this is sort of the same function. But what would make sense, however, is to partially apply to 1. So now you have a decrementing function, whatever, that can decrement 1 from whatever number we pass it, right? Which is, again, like actually useful, because you might want to map decrementing, you might want to map the function decrement over some x's, right? And I tried to think about like a few scenarios where partial application is like, where we can see how it's like clearly useful. I mean, hopefully you can see here how it's like clearly useful. But another one that I immediately think about is for example the fact that we can use add in this way, right? So then it's curried, but you can also define, let's say, the function sum. So let's say we have the list x's here. What if I want to compute the sum of all of the values within this list, right? But so that's actually it's a fold over add, or it's a reduce over add, right? Like fold and reduce is the same thing. So it's something like reduce r.add. So also let me just say that we defined sub. No, okay, sorry, we were working with sub. But anyways, I mean, Ramda has r.add and r.subtract and all of this stuff. But so there's no point in us actually defining sub and c sub. But we did that just for the sake of the example. But anyways, what you can do is you can say reduce using r.add starting from 0 and then over these x's, right? That gives us the sum, right? Is that correct? 10 plus 20 plus 30 plus 40. Yeah, it's correct, right? So we're successfully computing the sum. Now, what's interesting is, of course, that it might make sense to have a sum function, right? You might use that a lot. So then you could say, let's define the sum function as the reduction of r.add starting from 0, right? Now you have a sum function. You can apply the sum function to 100. Actually, I missed it. Oh, sorry. Of course, you can't have the sum of 100. Sorry, my bad. I mean, or you can't compute the sum from 100. You can compute the sum from the list x's, right? This is x's, but you can now compute the sum of any list. Like here's a list, right? Here's a list. Here's another list. Here's another list. They all work, right? You can compute the sum of these. And that works because we could partially apply the function reduce, right? Because reduce is partially applicable. It's curried. So because they've curried the function reduce, you can partially apply it, create a completely new function, and then pass that function around. And like, again, like you might immediately or spontaneously think that this is sort of gimmicky, and you're like, well, this isn't like, okay, fine, you can construct like your own increment function or like your own sum function, but like it's everywhere. Like as soon as you start to do this, you're like, but how did I ever really write code without partial application? So if you're interested, maybe you could check out my series on where I develop JavaScript games using functional programming, and I try not to use libraries. So then, I mean, partial application is so important in my mind for functional programming that I simply don't define multi-argument functions. I just define everything as a one-argument function because I don't want to have to define this messy curry function, because that would just, like, it would make it a bit bloated, right? And you don't actually need it unless you want this kind of nicer syntax, and unless you want your functions to interoperate, to be interoperable, I guess, with like the native JavaScript functions, such as, for example, reduce and so forth. But I just redefine all of these functions as one argument functions because currying is worth it. Like partial application is worth it for sure. So if you want to see more examples of partial application, I would highly recommend that series. I'll put the link in the description. If you as a viewer have examples of when partial application is, or like examples of how you can show or emphasize how partial application is so powerful and so useful and so fundamental, please do shoot something in the comments. I mean, that would be massively appreciated. It's tricky to find good examples. I mean, clearly another one is, of course, that you can use pipe and compose, and we've talked a bit about, I guess we've talked about compose, right? But yeah, you can use pipe and compose, so you can compose multiple functions. And again, that too is possible because of partial application. Getting point-free functions is possible because of partial application. Like, it's everywhere, right? So like, let's say you're parsing some kind of a log file, or you're no, actually, maybe that's a bit obscure. Let's think about it this way. Maybe you're getting a string from some input data that the user has typed in a field, like a phone number, right? And you want to sanitize this phone number. So like, you construct this pipeline where first you trim all the white space, and then let's say you turn every character into a lowercase character because you don't want to check for, actually that's a bit silly, but so let's say this is a name, maybe, right? So it's a username, and you don't want capitals in the username, so you trim the white space, you lowercase everything. I don't know, like you would do a bunch of other stuff here. I don't even know what. Yeah, maybe you run some regexes over it, you replace some invalid characters or whatnot, right? And here, to lower happens to be a function that actually takes, okay, so this is a bit silly because these are non-partially applied functions, because we don't, they're unary? Yeah, they're unary functions, both of them, because R2 lower takes one argument and trim takes one argument, so that was a bit silly. But you could have partially applied functions, so let's say you would have like a replace. I don't know if they actually have, let's look at this. Do we have replace here, which takes a string and a regex? Yeah, super good. So like, you could use r.replace, and then you would replace, you would add a regex, right? And you would replace strange characters such as maybe bang, or like anything that's not alphanumerical, and you would just replace that with empty an empty string, for example. And then you would partially apply the replace function, so that when you then pass whatever value, whatever string you have through your pipeline, you would get back, or you would completely apply that function, so that thing would be passed through the replace function, and that it would be passed to the replace function as the second argument, and then that replace function would be completely applied, and then you would get the result of that. So you would run it through the regex. I mean, what can I say? Like, this is revolutionizing at the very least, right? It's fantastic. It's fantastic, right? If you've probably already worked with partial application, but if you've stuck this far in the video, maybe potentially you haven't, or maybe you haven't really dug deep into it, definitely do it. It's completely worth it, right? And if you're a person who also loves partial application, please do shoot something in the comments and I don't know, show us the love. No, but like, share your experiences, please, right? That'd be fantastic. Anyways, let me try to wrap it. Oh my god, sorry, I missed. So we were talking about currying. I've talked about this before, curry and R.curryN, right? I've talked about another function where they had something and then something n. Let me super quickly say, R.curryN here returns a curried equivalent of the provided function with the specified arity. So the point is that if you have a variadic function, it's impossible to determine when a function is completely partially applied, right? Like if you have so JavaScript has math.max, for example. So math.max is a variadic function because you can keep passing values to it and it will just take whatever highest number it was passed from all of these arguments. So because it's variadic, like it takes any number of arguments, when is it partially applied enough, right? Like, so if you have a partially applied version of math.max, when you say math.max 10, you would expect to get a function back to which you can pass another argument, right? But if you then pass 20 to that function, should you then get a function or should you get 20 because that's the max number? And if you get a function, if you then pass 30, should you then get a function or should you then get like a number, right? So, and this problem is like indefinite. So there's no point where we can say, oh, it's now fully applied. So if I'm not mistaken, correct me if I'm wrong, but I think in like Haskell, for example, you don't have variadic functions because of this problem. Like, how could you possibly know that the partial application is over, so to speak, when you have a variadic function? But anyways, so the way they get around this, because variadic functions are used quite a lot in JavaScript, is that the way that Ramda gets around this is that they introduce curryN. So you can use curryN to then curry a function. So if we say if we do this, if we say just curry math.max, and then let's just run that function, right? No, sorry, let's say, let f be, okay, f equals r dot, because I've already used f. R.curry math.max, okay? So f, let's say f.length, for example. Its length is 2, okay? So actually, what's the length of math.max? Oh, sorry, math.max length. Yeah, okay, so because math.max reports a length of 2, and this is why they curry it up to 2 arguments. But math.max can actually handle way more arguments. But so now our f function, which we should have called, I don't know why I didn't call it max, so let me just call it max. Let max be r.curry of math.max. So if we call max on 10, then we get back a function because we are expecting another argument, and if we then pass 20, we get the highest number. But then we can't pass 30. Right? Because then that would be equivalent to calling, like treating 20 as a function and passing 30. Like that just makes no sense. So yeah, it's no longer variadic. But if you wanna, so what you can do is you can use curryN instead, and so you can say, okay, well, max is a function where I say r.curryN. It's a curried version of math.max, but where I'm expecting to pass 10 arguments. So it can be partially applied 9 times, and then when you pass another argument, then that's the final value, right? So max.length is now 10, and if you then, so you can pass, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you get back still a function. But if you pass another number to that, then you get a number, because then that's the final value. So then it's no longer variadic, of course, right? But again, as we said, like you can't have a curried variadic function, because when is the partial application completed? Okay, hopefully that makes sense. That's it. Let me wrap this up now, or I mean, let's consider this wrapped up. Thank you super much for watching. Remember to subscribe so that you won't miss the next Ramda video. Glad to have you along. Shoot any comments that you might have in the comments, and I will see you in the next one. Thanks for watching.